Next we'll start the next chapter, that is mole concept and stoichiometry. Mole concept and stoichiometry. First we'll do mole concept. Before going to moles, we need to understand something else, then we'll go to moles. Now in class 9 we have studied about solid, liquids and gases, difference between solid, liquids and gases. Solids have a definite shape, liquids do not. Gases take the shape of the container, even liquids also take the shape of the container. All these things you have studied, I am not going in details about it. Then you studied about the laws, the Boyle's law, the Charles law and the gas laws. Got it, the combined gas equation, so to say. Now here one thing you need to remember, that when you are doing the problems, because this chapter is basically a numerical chapter, completely a numerical chapter, hardly you will get some definitions here and there. So when you are doing the numericals, certain things you should keep it in your mind. It might have been told to you in class 9, alright, but still then I will say you, if the temperature is given in degrees Celsius, if it is given in degrees Celsius, you need to convert it into Kelvin. How you do that? T degree plus 273, then the temperature gets converted into Kelvin. That you must remember it first of all. It has to be converted into Kelvin. Whichever the question is given, you need to convert into what you can say Kelvin. Alright, and finally when you are taking out the answers, let us say you are being asked to calculate the temperature, then you need to subtract 273 from the Kelvin temperature. You will subtract 273 so that the answer you will get in degrees Celsius. Alright, fine. This is point number 1. Point number 2, you are supposed to what you can say calculate the pressure in terms of ATM if at all is given, or you need to convert into ATM if it is given in millimeter or centimeter. Alright, that is 1 ATM is equal to 760 mm of Hg or 76 cm of Hg. 760 mm and 1 ATM is equal to, remember it as 1 torr. Torr means Torselian. Torselli was name of scientist. Alright, that is from here we got it, torr, 1 ATM is. Alright, so in this way we can say that 1 ATM, rather I should say that is nothing but 760 mm or 760 torr, we can say that. Clear, instead of 1 torr I can write it as 760 torr. Generally this is not being used in class 10 so much, but ATM and all these things will be used accordingly, we can say that. Clear. Next is, after that that is you are getting the unit of volume. So volume is measured in liters. 1 liter is equal to 1000 ml is equal to 1000 cc, we can say that. That means 1 ml is 1 cc and 1 liter is 1 decimeter cube. 1 liter is 1 decimeter cube, we can say that. Alright, 1 liter is 1000 ml is equal to 1000 cc. Cc means centimeter cube. And 1 ml for that is, and 1 ml is equal to 1 cc, and 1 liter is 1 decimeter cube. So these are the things you need to know. Here I said 1 torr, it's not 1 torr, by mistake I said it is 760 torr. Alright, yeah. So in this way, these are the units, you should know it. While doing the numericals, you have to convert it. In certain times you need to convert it. So at that time you need to do this particular things. Okay, fine. Now next is, after that we'll come to the laws. Let me just tell you the Boyle's law, Charles law and the combined gas equation. So Boyle's law says that pressure is inversely proportional to volume when temperature remain constant. We have studied. When temperature is constant, pressure is inversely proportional to volume. So P is equal to K into 1 by V. So PV is equal to constant. So P1 V1 is equal to P2 V2. This is your Boyle's law which you studied. Boyle's law, this one is. This is a formula you need to remember. When temperature remains constant, pressure is inversely proportional to volume. That means volume increases, pressure decreases, or volume decreases, pressure increases. Got it? So this you studied in class 9. Just once I am revising it because you will be needing this one later on in the chapter. Next is Charles law. Charles law says that volume is directly proportional to temperature, Kelvin temperature or absolute temperature. We can say that when P is constant, when pressure is constant. Alright, when pressure is constant, volume is proportional to absolute or Kelvin temperature. Absolute temperature is nothing but on a 0 Kelvin, which is minus 273 degrees Celsius. Why do we call it? Because that is the lowest temperature. Listen carefully. That is the lowest temperature attained by any gas. Of course, no gases till now has attained that particular temperature. So for that reason, Lord Kelvin has said that is the lowest attainable temperature attained by any gas. Why? After that, what it happens? It does not remain in the gaseous state. It either gets converted into liquid or solid state, depending upon the nature of the gas. Depending upon the nature of the gas. So that is the lowest attainable temperature. And when there is a change of state, you know that kinetic energy becomes zero. So it is said that the molecular motion ceases to zero below minus 273 degrees Celsius, that is 0 Kelvin. Molecular motion ceases to be zero. We can say that molecular motion ceases to be zero. So hence we say that particular temperature as Kelvin temperature or absolute temperature, because this temperature was found out by Lord Kelvin. Alright, Lord Kelvin. So hence we call it as Kelvin temperature, because I said you that is the lowest attainable temperature attained by any gas. Below this temperature, the gas does not remain in the gaseous state. It either gets converted into liquid or the solid state, depending upon the nature of the gas, we can say that. And at this particular temperature, the molecular motion ceases to be zero. We can say that the molecular motion, because change of state is going to take place now. So molecular motion ceases to be zero. We can say that. Clear? Okay. So V is equal to KT. K is equal to V by T. So V1 by T1 is equal to V2 by T2. This is the Charles law, we can say that. Here the temperature has to be converted into Kelvin. Already I said it. Alright, temperature has to be converted into Kelvin. And all these gases, remember that the gas should be a dry gas. It should be a dry gas. The definition goes in this way. The definition goes, for a given mass of a dry gas, volume is directly proportional to temperature, absolute temperature or Kelvin temperature, when pressure remains constant. Mind it, it should be a dry gas, because if it is a moist gas, then the gas laws is not obeyed. Why? Because if the gas is moist, then the gas may not remain in the gaseous state. It may convert its state. For example, ammonia, if it is moist, it changes into ammonium hydroxide. Is it a gas? No. HCl, when it is moist, it changes into hydrochloric acid. Is it a gas? No. Alright. Carbon dioxide, when it is moist, it changes into carbonic acid. Is it a gas? No. Sulfur dioxide, when it is moist, it changes into sulfurous acid. It is a gas? No. In this way. For that reason, when you apply the gas laws, the gas has to be perfectly dry, because it may or may not remain in the gaseous state. And if it does not remain in the gaseous state, you can't apply the gas laws. For that reason. Now, next is, in this way, you get the Boyle's law and the Charles law, which you already studied in class 9. Alright. Now, let me add up these two laws. That is, from the Boyle's law we get it V is inversely proportional to P, and from the Charles law we get it V is directly proportional to T. So, V is directly proportional to T by P. We can say that. Now, V is equal to KT by P. So, K is equal to PV by T. That is nothing but P1 V1 by T1 is equal to P2 V2 by T2. Here, you remember that here what you find is that the temperature should be in Kelvin, mind it. Alright, and here one term is there, generally we use it in the perfect gas equation, STP or NTP, both are same. STP means standard temperature pressure, NTP means normal temperature pressure, both are same. Right, temperature is 273 and pressure 273 Kelvin, and pressure is 180 m or 760 mm of Hg. Alright, or 760 torr, we can say that. Same thing. So in this way, if it is at STP, let us say if this particular one is STP, means what? Pressure and temperature is at STP. V2 you need to find. So pressure will be 760 mm if the question is going in mm, or 80 m means 180 m, and temperature will be 273 Kelvin. Alright, that you need to remember it. If it is at STP, generally everything is measured at STP, standard temperature pressure, normal temperature pressure, we can say that. Alright, so at that particular temperature should be 273 Kelvin and the pressure should be, as I said, 180 m or 760 mm. Alright, generally we use it. So in this way, this is about your the part which you have already studied in class 9, which I discussed with you. Now I am going to come to, that is what is there in class 10, we can say that. Clear? The first is your Gay-Lussac's law. Gay-Lussac's law. The first law is Gay-Lussac's law. It is being said that Gay-Lussac's law of gaseous volume. The complete sentence is Gay-Lussac's law of gaseous volume. What is the law? When gases react, they do so in volume. correct? Whenever gases react, they react in terms of volume. Got it? And what I said, when gases react, they do so in volumes, which bears a simple whole number ratio to one another. Got it? They bear a simple whole number ratio to one another. Suppose two reactants are there. For example, suppose nitrogen gas and hydrogen gas is there. So N2 plus 3H2, we can say that. Let me write 3 later on. N2 gas and H2 gas. So it is 1 mole and here it is 3 moles. Generally they react. So what is the ratio? 1:3. They react always in a simple whole number ratio. Have you seen ever here we are taking 1/3 nitrogen or 5/6 hydrogen? No, it is never fractional. It is always a whole number. Why? Because generally atoms and molecules cannot be fractional for that reason. Alright, basically atoms. Because when we are saying this is nothing but when we are balancing it, the equation, what we balance the atoms. But of course we are writing the molecules here. Alright, so hence for that reason it is never fractional. Theoretically we can write it down for balancing. You can write, but practically it is not possible. Alright, so hence we said that when gases react, when they are reacting, they do so in volume. Yes. How we speak this one? 1 volume of nitrogen reacts with 3 volume of hydrogen. We speak in this particular way. We speak in this way. Suppose the volume is given in liter. Let us say 1 liter of hydrogen and nitrogen reacts with 3 liters of hydrogen gas. We can say that. So you speak in terms of volume. So when gases react, they do so in volumes, which bears a simple whole number ratio. For example, we can take another one. H2 gas plus Cl2 gas. We can say that. Alright. When gases react, they do so in volumes always. What is the ratio here? 1:1. 1 volume, this is 1 volume. This is 1 mole, this is 1 mole. Mole I am not saying you because you have not studied. For that reason I am not using the word mole. When you study mole, we will be using the word mole. It is similar to that of volume only. Alright. So when gases react, as you can see, they are reacting, they do so in volumes always. Mind it. We measure the gas in terms of volume only. We don't measure in terms of gram and all these things. Definitely not. Yeah, it is measured in terms of liter or milliliter or cc or decimeter cube. We can say the units of volume. Yeah. They do so in volumes, which bears a simple whole number ratio, as you can see there, to one another and also to the volume of the product if gaseous. Also to the volume of the product if it is gaseous. Like here N2 plus 3H2 will give you 2NH3 gas. Yes, I can say 1:3:2 because 2 ammonia, it's a gas. Alright, here H2 plus Cl2 will give you 2HCl gas. Yes, so we can say 1:1:2. We can say that. Clear? And also to the product if gaseous, provided temperature and pressure remaining constant. Throughout the experiment, temperature and pressure will remain constant. Got it? What I said? If gaseous. If gaseous means, now I am giving another example here. Let me rub it this one, then you will come to know. Of course, you have understood this one. Now, here suppose I am taking, that is H2 gas plus O2 gas will give you, that is nothing but H2O liquid. Now to balance it, 2H2 gas gives 2H2O liquid. So here the ratio will be here the ratio will be 2:1. 2:1. I will not take this. Why? Because this is liquid. This is liquid. What I said you? And also to the volume of the product if gaseous. If the product is a gas, then only I will consider it. If it is not a gas, I will not consider it. So in this particular case, in Gay-Lussac's law, mind it, the product may be liquid, gas, solid, whatever it is. If it is a gas, we will consider it, like I have considered. If it is not a gas, I will not consider it. But the reactant has to be gaseous. If the reactant is not a gas, let us say this particular equation, C solid plus O2 gas gives CO2 gas. Now in this particular equation, Gay-Lussac's law is not valid. Why? Because the reactant is a solid. How will I take the ratio? With one component, can I get a ratio? No. So the reactant has to be gaseous. The product may or may not be a gas. Listen carefully. Product may or may not be a gas. Like here it is not a gas. No problem. I will take only the reactant. But the reactant has to be gaseous. Because if the reactant is not gaseous, then how will I find the ratio? We will not get a ratio at all. Alright? And moreover, the law is Gay-Lussac's law of gaseous volume. It is not solid volume or liquid volume. Alright? So hence this law is not true for solid or liquid. That's the most important thing you need to understand here. If it is solid or liquid, we ignore it in the product. But if it is in the reactant, it is not at all applicable. Finished. Alright? So in this way, Gay-Lussac's law says when the gases react, they do so in volumes, as you can see, and to also to the volume of the product if gaseous, provided the temperature and pressure remaining constant, we can say that. And here when the gases react, they do so in volumes which bears a simple whole number ratio. Yes, always the ratio you can see is simple, it's never fractional, because the atoms and molecules cannot be fractional, we can say that. Now some numericals are there upon it, alright, but before going to the numericals, let us move one more law and then we'll go to the numericals. Okay, thank you.